Okay, so here we are in Chapter 7, Section 2, and we're going to start off just by defining a couple things. And we already should have an idea of this because we kind of seen it over in chapter 6, I think. No, Chapter 5. The sampling distribution of a statistic is the probability distribution for the possible values of the statistic. Now, we saw probability distributions in Chapter 5, whether it was discrete or binomial, okay? And there are three ways to find the sampling distribution of a statistic. So we're talking about samples here. We're not talking about a population. And we really need to start thinking about the differences between the sample and the population. Okay? Remember in the previous lecture for chapter 7, a parameter is a numerical measurement about a population. And a statistic is a numerical measurement about a sample. And sometimes it is virtually impossible for us to test the entire population. So what we do is collect samples. So then the question becomes, okay, well, what do we do with these samples? I'm going to show you here, okay? So there are three ways to actually find sampling distributions of any statistic that you want. The first one, So number one, you can derive it mathematically. Okay, so I'm going to show you how to do this. Number two, you can use some sort of a simulation. And I'll show you one that looks like that later. And then the third way, which is kind of beyond the scope of this course, which is using statistical theorems. So you may have to use a theorem and apply it to a sample that you've collected, or you got to create your own theorem, which, like I said, that's beyond the scope of this class, but that's fine. What we're really going to be focused on are the first two: derive it mathematically, and then using a simulation. Like I said, I'm going to show you how to do both. So for the first one, I'm going to write down a problem, and then we're going to go ahead and figure it out. Okay, so here's our problem right here. So a population consists of n equals 5 numbers, and those numbers are going to be 3, 6, 9, 12, and 15. If a random sample of size n equals 3 is selected without replacement, find the sampling distribution for the mean, x bar, and the sample median. Now, there's a lot of things happening in this problem. First, in the first sentence, I'm using the capital letter N equals 5. So remember, the capital letter N stands for the population. And then in the second sentence where it says, if a random sample of size n equals 3 is selected, notice I'm using the lowercase n because that stands for a sample. So we have two things going on here. We have a population, 3, 6, 9, 12, and 15. And then we have the sample. Now, what we're going to be doing here is this. We're going to be selecting 3 numbers at random without replacement. Our goal is to find what the sampling distribution for the mean and the median looks like when you select 3 numbers, okay? So first, what I want to do is let's just find the population mean and let's find the population median, okay? So the population mean, remember, is mu, and that's just going to be adding up every single number that we have in our population and then divided by the total number we have. So 3 plus 6 plus 9 plus 12 plus 15, all divided by 5, equals 9. Okay? Now, the population median, which is a capital M. All right, well, luckily for us, 3, 6, 9, 12, 15, it's already in numerical order. I have an odd number, so I can just look right in the middle, physically in the middle, and I also get a median equal to 9. Okay? So that's the first easy part, just figuring out what the population population parameters are. Now let's look at the sample statistics, okay? So what we need to be able to see, and I'm going to write these numbers out again, 3, 6, 9, 12, and 15. Notice that in the problem, they wanted us to select at random without replacement. So select at random without replacement 3 numbers. All right, so this is a combination. Order doesn't matter. We just know we're not replacing numbers that we pick. So this is going to be a combination of 5, choose 3. Okay? That's the first thing. So 5 choose 3. If we were to do the math on that, that means there are 10 possible outcomes. For example, we can select 3, 6, and 9 at random. We could also select 3, 9, and 12. We could also select 6, 15, and then 9. Okay? So this is what we're talking about when we have all these different possible outcomes. Now, what are we supposed to do with these? Well, we're supposed to find the mean for each of them. So, for example, with the first one, this is going to be 3 plus 6 plus 9 all over 3. And that's going to equal 18 divided by 3 or 6. Okay? We can also do the very last one here. That's going to be 6 plus 15 plus 9 all over 3. Well, let's see here. That's going to be 30 over 3, which equals 10. Now, why are we doing this? First, you got to understand this is a very small, simple problem. Okay? What if we were trying to find, this is an island here, and this island is huge. It's the size of Australia. It's massive. It's like a continent, okay? And we're trying to find the average weight of a kangaroo. You cannot select every single kangaroo. You just can't do that. So what we do is we get little samples, sample 1, sample 2, sample 3, and within those samples, we're going to randomly select 5 kangaroos and then average their weight. So within sample 1, you may have, and I'm going to zoom in here, you may have X bar 1, X bar 2, X bar 3, which means you selected 5 random kangaroos, and you added up their weights and divided by 5, and you got the first mean. Then you did that for the second group, and you did that for the third group within the first sample. And you did that for sample 1, sample 2, sample 3. See, by doing this, what we're doing is we're randomizing everything, and it's going to give us a probability distribution. It's unbelievable what happens when you actually do this. So let's continue with this problem because, like I said, it's a very simple one. But what I'm going to do here is I'm going to just write out the table of all the possible outcomes we can have. Now, remember, there's only 10, so there's not a lot. So I'm going to pause the video, write out the outcomes, and then we'll do some math with them, okay? Okay, I'm back, and here's our table. So if you want, you can write the table down, or you can just watch. I'm going to go ahead and just explain it. So in the very first row, we have our first sample. We randomly selected 3 numbers. Turned out to be 3, 6, 9. So what I did is I went ahead and calculated the mean, which is 6, and the median, which is also 6. Then I did it for the second sample. So that second sample, the random numbers are 3, 6, and 12. When you find the mean for 3, 6, and 12, that answer is 7. And then the median is going to be 6. For the third sample, the random numbers selected are 3, 6, 15. When you average them, you get an 8. The median is 6. And I did that for every single combination of sample values that I can get. Okay? Now, here is the most amazing part about this. Okay? Let's go ahead and find the probability distribution for this, all right? Or the sample distribution of the statistic, okay? So what I mean by that is, what's the probability of getting a mean that equals 6? Well, if you look at the possible outcomes, there are 10, and only one time did I get a 6, so that's going to be 0.1. And I'm going to do this for each one of these, okay? So what's the probability of getting a 7? Well, if you just scan, that's also 1/10, so that's going to be 0.1. What's the probability that the mean is going to equal 8? Well, let's see here. We have 1, 2 of them, so that's going to be 2 over 10, or 0.2. And then the probability that the mean equals 9, well, let's see here. That's only one of them. Or wait a minute, is it 2? Oh, nope, it's 2. I'm sorry. Can't count, obviously. So that's going to be 0.2. The probability that when you average the 3 numbers, you get 10. Well, that's also going to be 0.2, or 2 over 10. What's the probability that the mean is going to be 11? Well, that's 1 over 10, 0.1. And then lastly, the probability that X bar equals 12. and that's also 1 out of 10, which equals 0.1. Okay, so all I did was just find probabilities of probability that the mean is 6, probability that the mean is 7, and so forth. Now, we'll worry about the median in a second. Here's what I want to do. I'm going to scroll over to the right because I want to be able to see these values. And I'm going to go ahead and create a probability distribution. Now, we remember from chapter 5 that when you create a probability distribution, your probabilities go on the y-axis, okay? Your outcomes, zoom out here a little bit, the outcomes go on the x-axis. All right? So we have 6, 7, 8, 9, 10. I need a little bit more space. 11 and 12. And then on the y-axis, 0.1, 0.2, and I'll put a 0.3 just in case. And watch what happens when I go ahead and start plotting these. Now, before I do this, I want to go back and just think about what's happening here. Okay? We had a population of 5 numbers, 3, 6, 9, 12, and 15. That's our population. When we applied the population mean formula, we calculated that the population mean is going to be 9. We also calculated the median to be 9. So then what we said was, okay, what if we just select 3 numbers at random without replacement, and we find their averages? So instead of looking at the entire population, you were only looking at a small sample. What happens when we find not only their means, but the probability of obtaining them? So that's what we calculated. And I'm going to go ahead and just draw it. So mean equals 6.1. Mean equals 7.1. Mean equals 8.2. Mean equals 9.2. Mean equals 10 is also 0.2. Mean equals 11.1. And then mean equals 12.1. Now, we had 5 total numbers in our population. We randomly select 3 of them, and we found that here's the probability distribution breakdown. This is the sampling distribution of our statistic, which we know is the probability distribution for the possible values of the statistic that results with random sample sizes of n. Repeated, I'm just reading the definition again. Random samples of size n repeatedly drawn from the population. And notice that although it's not perfect, and it's not perfect because we have a very, very small population, it's only 5 numbers. But this basically has a bell-shaped curve from chapter 6, which is exactly what we want with a normal distribution. And if you have simple random sampling at its finest, at its purest form, you will get a bell-shaped curve almost every single time. And that's what this is all about when you sample things. So you want to make sure that when you're sampling data, you're doing it in a responsible way. And if you've done it in a responsible way and you start plotting down these probability distributions, you're going to get a bell-shaped curve. And that is going to lead us into the next section, which is that central limit theorem, which says, okay, if the sample size is large enough, regardless of the sampling technique, you're going to get this bell-shaped curve. It just so happens that if your sampling technique is garbage, it's really hard to do because you're going to need an extremely large sample size. However, if your sampling technique is really good, it turns out that the number of samples that you need is only 30, which is absolutely astounding. Okay? So before we move on, let's go ahead and let's see what happens when we do the median, because we were also asked to do the median. And watch what happens when we do this median. So give me a second. I'm going to pause the video. I'm going to erase what I don't need, and then we're going to find the probabilities of the median. I think you know where this is going, okay? But just watch. So let me erase. I'll be right back. Okay, and I'm back. So we're going to do the median now. So what's the probability when the median equals 6? Well, that's going to be 3 over 10 or 0.3. What about the probability when the median equals, we'll say 7? Well, that's going to be 0, because if you just scan down your median table, there are no number zeros. There are no number 8s either. So that's a 0. What about when the median equals 9? Well, let's see here. There's 1, 2, 3, 4. So that's going to be 4 over 10, which we know is 0.4. Oh, sorry, I'm moving too fast. What about the probability when the median equals 10? Well, that's going to be 0. What about the probability when the median equals 11? That's also going to be 0. And then the probability when the median equals 12. 1, 2, 3. So that's going to be 3 over 10, which equals 0.3. You have no idea how excited I am right now. Because when I go ahead and draw my probability distribution, remember the outcomes goes along the x-axis. This is going to be the probability of obtaining the median now. I'm going to go 0.3, 0.4, 0.5, and then 6, 7, 8, 9, 10, 11, and 12. Okay, here we go. When the median is 6, we come out with 0.3. 7 is 0. 8 is 0. 9 is 0.4. 10 is 0. 11 is 0. 12 is 0.3. And look at that. Wow. That is a nice... Oh, that's a horrible looking bell. All right. There we go. Once again, we're getting that nice bell-shaped curve. Okay? So I hope this makes sense. That's what this is all about. Now what we're going to do is we're going to look at the central limit theorem and then how that applies. But that's going to be in the next video. So good luck with this chapter. It's not too difficult. It's just you got to think about outcomes and stuff like that. The problems I picked are kind of small, and if you follow this method that I used, you should be okay. The hardest part is just going to be right here in the middle. It's going to be this. It's going to be finding the sample values. That's going to be the hardest part. But I tried to choose problems that had like very small sample sizes or very small population sizes. Okay? See you next video.